Okay, I used some unfortunate notation in the preceding. There's nothing wrong with anything that I did, except that when I called this x, that would be really easy to confuse with the x component of a vector, and that was not the intent. I simply used x because that's kind of a standard notation for a position function. But when you're talking about motion in 2 or 3 dimensions, it's better to use something other than x. So I'm going to change my x's all to r's. It's going to be a little messy. But I think we kind of need to do that. So we have now an r of t function instead of an x of t function, and we're more used to thinking of the position vector as an r vector. Now I've got my incline here, and I've indicated my r of 0 vector, which for the previous was 10I plus 2j. So I'm going to, we don't know where the origin is. It's somewhere back off of the incline here, but this initial position vector allows us to locate the position at which I'm going to release this ball. Now I'm going to start this ball in the direction of this vector here. This vector makes an angle which I presume to be about 30 degrees above the horizontal. And my initial vector v of 0 then, okay, I'm going to assume, again, the angle's 30 degrees, so that the cosine of theta and sine of theta will now be cosine and sine of 30 degrees. And I put 10 out in front of here. Now I don't want to carry units along, although if we were doing the physics, we would probably want the units. But I'm going to try to roll this thing at about 10 centimeters per second. Actually, I'm probably moving faster than that. I'm going to guess that that's more like 40 centimeters per second. Don't really know. And this is just for the purposes of illustration, but here we go. I'm going to roll this ball, and I'm going to watch its path. Okay. Now, I can kind of trace the path. What did the ball do? It came up here, pretty soon came down below horizontal, probably came up a little further than I'm indicating there. But we see that we get this curved path. And probably can't actually follow that path very well, but let's try. Yeah, a little faster. There we go. We stayed along that path pretty well. Okay, so that's a very plausible path for the motion of this ball. Now we want to bring that back to within the context of our vector function. Remember, our vector function now is r of t equals v naught cosine theta times t times I plus v naught sine theta times t minus 1/2 g sub d t squared j plus our 10I plus 2j vector. And I should have distributed that within the I and the j component. I'll do that in the next step. Now the conditions that we have for this problem, as we've described them, as soon as we recover our camera's focus. For the assumed problem, we had v naught equals 10, theta equals 30 degrees. So that our r of t function would be 10 cosine of 30 degrees, and I'm going to put my 10 back in here, plus 10 I plus 10 sine of theta, sine of getting late, that should be 30 degrees times t minus 1/2 g sub d t squared plus r2 times j. Now if we want to, the cosine of 30 degrees is square root of 3 divided by 2. That's approximately 8/7, and I'm going to use the approximation since nothing we did with the actual projectile was perfect. There's no point in making these numbers perfect, except I do want to go ahead and insert my t here. Okay, so I have 10 cosine of 30 degrees. Well, that's about 8.7 t plus 10 times I. And to that we're going to add 10 times the sine of 30 degrees. Sine of 30 degrees is exactly 1/2. So that's 5t minus 1/2 g sub d t squared plus 2 multiplied by j. That should be the r of t function for our motion. I could estimate the coordinates of a point over here and the time it took to get here. I would say that relative to this point, well, I'm not going to actually do it, but I could get my, let's just say it took 1.5 seconds to get here. I could fill in the question marks, have r of t equal to some function of I and j at 1.5, and plugging in those components, I could solve for g sub d. There's a number of other things we can do. We can find the shape of a path. We can analyze the velocity function, the r prime function, just by taking the derivative of this function. We can get back to the acceleration function. Of course, everything will drop off when we take two derivatives, and we'll be back to the acceleration function we started with.